Thanks so much, Monitorama. I'm very happy and proud to be here at Monitorama in Portland. What a fantastic conference, right? I mean, like, we already had a round of applause for Pete and Jason, but give it up. Like, tireless. Okay, let's talk about theory. Theory is something that's always present in our work, but it often goes unmentioned, uncommunicated. But I'm going to show you that by building out your observability with a theory of the system in mind, you will understand your system far better and your team will understand what you're talking about far better. And understanding your system translates to better decisions and more uptime. I'm Dan Slimmon. I've been an SRE DevOps sysadmin since 2007, so a little over 16 years. Recently, I was at Etsy. I was on the observability team at Etsy, and then at HashiCorp, I was a staff SRE on the production engineering team, where our job was basically just sort of find weird shit happening and figure out what it is. It was really fun stuff. My company is D2E. D2E is providing training for training and consulting and incident response, incident analysis. Check us out. That's the website, d2e.engineering. And so let's start with the control theory definition of observability, which was roughly if a system's observable if one can determine the behavior of the entire system from the system's outputs. And that one can determine is doing a lot of heavy lifting. So who is one? How precisely does this one need to be able to determine the behavior in order to call the system observable? And I feel a little like Bill Clinton here, but it also depends on what the meaning of the word can is, right? Does it mean one can determine the behavior in principle by using some inference chain that they may or may not have on hand? Or does it mean that the system's behavior is reported directly by the outputs and you can interpret it no matter which operator of the system you are? I would argue that in all cases, in order to observe the system's behavior, you need to make sense of the data that you have at hand, and that sense making is an active process, and it requires a theory. So theory is a mental framework that tells you what relationships to expect among the system's outputs, and you can use a theory to infer more general facts about what the system's doing, but from its outputs, right? So in a way, the system has some fullness of behavior that it compresses down to a finite set of outputs, and then the theory is what you use to decompress that data back into your head to form an understanding. And to the extent that that decompression is lossless, you have an observable system. That's how I think of it, at least. Essentially, the theory is what you use to convert data into understanding. So for example, let's say you're sick. You've been having lethargy, muscle soreness. It's been getting worse over the last 48 hours, so you decide it's time to go to the doctor's office. And you're sitting in the doctor's office, and this looks very promising. He's got a huge collection of medical books that look well thumbed. There's a bunch of impressive looking diplomas on the wall from top tier schools. And you're waiting, and you're waiting and waiting. And the doctor finally walks into the room, and he doesn't even look up from his clipboard. He says, "You have Duchenne-Borley syndrome." He takes a bottle of pills, puts it on the desk in front of you, and says, "Take 2 of these daily, call me in 4 weeks." And he walks out the door. And you look up and say, "But doc, I haven't even told you about my symptoms." He's already gone. You say to yourself, "Well, that wasn't a very good doctor." So you decide to get a second opinion, right? And go to a different doctor. And this doctor says, "Okay, first I need to take a history. This will take about 4 hours of interviews. We'll go through every medical event in your life, as well as every non-medical event." You say, "Okay." And this doctor says, "Also, I need you to spit in this cup, pee in this flask, cry into this handkerchief, and I'll need about half a cup of your blood." So this doctor proceeds to run every possible medical test there is, which takes a very long time. And when she finally calls you in to discuss the results, she says, well, your white blood cell count is normal. Your PGX is 14.92 plus or minus 0.3. You have 2 full arms, 5 fingernails per arm. Your Dipsy-Fleberton index is in the upper thousands. You go to try to talk to her, and she keeps going. She says, however, your Flipsy-Deberton score is all the way in the purple range, and your brain temperature is an 8 out of 10 on the Idaho brain temperature scale. And she goes on like this for a while. She keeps talking. Finally, you get a chance to say, but doc, what does this all mean? She looks at you blankly, says, mean? Right? So these are both very bad doctors, but they're bad for different reasons. The first one with all the books and the diplomas who didn't even ask you what your symptoms were, was all theory, no data. This is like if the developers building your product were so confident that their code was correct and their tests had full coverage that nobody even bothered to build any telemetry in it. It's going to work in production. Don't worry about it. The second doctor, with all the tests, was all data, no theory. And without theory, you can't have meaning. This would be like if we enabled every telemetry source, logged the inputs and outputs of every function call, monitor all the things, but could never make heads or tails of the data because it's completely disorganized. My contention is that in most orgs, lack of data is not the bottleneck to observability. The bottleneck is an insufficiently developed or insufficiently maintained theory for interpreting the data that you have. We have dashboards with a dizzying amount of graphs on them, but our eyes glaze over when we scroll through them because it's just too much. We get pages that tell us that some number went over some other number. We have to construct our frame of reference for what that means on the fly. And in general, we're much more like the second doctor with all the tests than we are like the first doctor with all the books. We need some kind of balance. But if this is true, if it's true that the bottleneck is usually a lack of theory or a lack of communication of your theory for how the system behaves, then it follows that if we want to improve our observability, generally, we should mainly be taking not actions that increase the amount of data that our systems produce, but actions that place the existing data into a useful theory for the user, for the operator. I think that, well, we'll get to that. So what are the actions that you can take to put data into a theoretical frame? In general, it comes down to presenting the data in a suggestive way, like posed on a chaise longue with a tastefully placed Chinese fan, in a way that suggests a theory to the person who's looking at the data. So things like juxtaposing quantities that are related to one another, where if you expect one to go up if the other goes down, things like that. Making context readily available to the person who's looking at the data, and presenting as little data as you can afford to while still having the person be able to make sense of what they're looking at. Because the best theory is the one that explains the largest class of experimental results with the smallest set of rules. So for example, graph dashboards. The most useful graph dashboard is not the one with the most graphs on it. I've heard a lot of people talk, and this is true, about how many of the graph dashboards that we look at are just a history of the incidents we have. We keep adding a graph every time something goes wrong, and that doesn't really add up to understanding, does it? I think we all know that from having seen those dashboards. You can add graphs all day, but your dashboard won't produce meaning unless it fits the data into a theory of the system's behavior that you can use to interpret the data. And we can make graph dashboards that are better at doing this. One way to do that is by organizing the dashboard into sections, and then each section contains the smallest possible set of graphs that you think will allow the user to evaluate whether what's going on is normal or not within your theory for that subsystem, right? So this should be familiar to everybody. The first section on a service dashboard should usually be essentially treating the system like a black box. So you have saturation, which is the number of requests, assuming this is like a service that serves requests like a web service or something. First one could be your saturation, how many requests are waiting to start being served, latency, error rate, and then throughput, the rate at which the requests are exiting the system. So this supports sort of a black box theory. And when you look at this, if these are the only graphs in that section, you can say, well, okay, the theory is requests come into the system, they wait, they spend some amount of time inside the black box, and they come out either emitting an error in the process or not, right? Any more graphs than this, generally, and you've made the theory a little messier. You have 8 graphs up here. Now, well, which graphs am I supposed to be looking at if I'm trying to interpret this thing within a theory? You've sort of combined too much theory, too many theories, it's a mess. So that's why you have more sections. So usually my second section on a service dashboard is like the developer's theory of how the system works internally. So we have things like cache hit rates, concurrent Go routines, and I usually work with a developer to try to squeeze their understanding into as few quantities as possible, which is often hard because they have many things to tell me about how the system works. And then usually have a few more sections that refer to like your theory of how the system interacts with other downstream services. So this scheme helps the user like make sense of the data because you've taken your theory of how the system works and you've sort of suggested it onto the dashboard. Other things you can do to make dashboards that communicate theory more effectively are don't use the default names of the metrics that come out of the storage system. Name it the thing that you would name it to somebody if you were having a conversation with them about the system, right? I like to have a notes panel. I really overuse notes panels. I have a notes panel in each section that explains how I think these metrics are going to react to each other under normal and abnormal situations. You want to have links to the upstream and downstream services that the thing talks to. You want to have, I like to have a consistent presentation of a particular kind of data. So for example, if I'm graphing an error counts, an error rate, I'll use a bar graph and have them be red everywhere so that it's just immediately apparent to somebody what kind of data they're looking at. What about monitors and alerts? How can those things be integrated into our theory so they're not just disconnected data that you're looking at and trying to figure out how do I hook this into things? Again, concise and accurate names is huge. Name the alert the thing that you would name it if you were talking to somebody without any reference to a computer in front of you. If you were just having a conversation with somebody, what would you call it? And you want to explain in the description of the monitor why the behavior that triggered the monitor was unexpected. Well, this number went over this other number. Why is that abnormal? What's weird about that? If you can explain what's weird about that, then you're sort of communicating part of your theory about how things normally are supposed to function to the person at 3 a.m. who got the page. Links are always good. Links to dashboards, links to log searches, links to traces, explaining within a succinct way why those things are relevant to the page that the person just got. And you want to aim, this is maybe a little controversial, but you want to aim to have a minimal covering set of the monitors, of monitors for a given component. So if you have multiple monitors that will go off in a given situation, or you can have, definitely, I think we all know, you can have too many monitors, and if you have too many monitors, then that's a sign to me of an unclear theory of how the system is supposed to behave or what pathologies it might undergo. Finally, incident response. Okay, so the incident response is one of the most interesting ones to think about theory, because if we're doing our jobs right, the thing that you just got paged about has never happened before. So it's very common during an incident response to get lost in data. Something's just happened that's never happened before, and I'm sure many of us have been on incident calls where we're sitting there for half an hour and everybody's just sort of scrolling through dashboards and logs and trying to hook onto something in the data that might give some hint of what's going on. And you have to construct your theory, which amounts to a diagnosis ultimately on the fly. And that's why I advocate for an explicit formal hypothesis generation during an incident response. If the cause is not obvious, like somebody deployed code and it immediately broke and then you got to revert the code, right? If you don't immediately know why the problem is happening, the incident lead should walk through a process with everybody where you explicitly list what the symptoms are that you've observed that you're going to be investigating today, throw them on a doc, everybody look at them, agree that those are the symptoms under investigation. You brainstorm some hypotheses that could explain that data, and then you take actions that you take actions that will rule out one or more of those hypotheses until you have finally taken an action that fixes the problem. This is called, doctors call this differential diagnosis, but we can copy what they do because they're working with a complex system that has limited outputs that they have access to, and they're trying to troubleshoot unexpected problems in that complex system, and so are we. So I think if you do this, if you center the creation of a shared theory on the call, then essentially lets you be a good software doctor instead of being like either of the two bad doctors that we talked about earlier. And before I cede the stage, I'm running a little short, so you're welcome. Let me leave you with one final piece of advice for developing your theory of the system's behavior, just overall. And that is this: engage with production anomalies as often and deeply as you can. At HashiCorp, what I would do is I would actually get volunteers from dev teams to come in to my team for a week, and we would just look for trouble. Bring up a dashboard for a system that this developer works on and cares about, and look at it until they say, well, that's weird. And then we would run that problem down. Sometimes we would run it down and we would realize, oh, this is normal, this isn't a real problem. That's not a waste of time when you do that, because every time you do that, you get to have a more robust theory in your head. You get to see what's expected and what's normal, what's not expected, what's abnormal, and that theory allows you to build intuition, which if you do that as a team over and over, you will be able to sort of get a sense for how your system hums, for lack of a better term. And the more robust your theory, the more meaning you'll have access to. Oh, and by the way, speaking of incident response, part one of my 3-part video course, Leading Incidents, launches today. And since you're watching this talk, you get 24% off. So go use that code, go to that website, check it out. And again, I just want to say, Monitorama is such a wonderful place to be. I have had an incredibly great time getting to know all you bright, creative, badass people. Thank you for making this the best tech conference there is.
All right. Do we have some questions before the break? I'm gonna get out of the light if I can see anything. Yep, right over here.
Do you have any advice for keeping troubleshooting narrowed down to just the theory that's being approached at the time, rather than constantly branching out into chaotic angles?
Advice to keep the thing narrow.
Yeah. So you can't just this process I described, where you list the symptoms, the hypotheses, and the actions, and you cycle back through. You can't just accept any hypothesis. Any hypothesis that gets proposed, it's only valid if it is explanatory for the symptoms and falsifiable. So you have to be, so if somebody's proposing hypotheses that either you can't really connect to the symptoms under investigation, or that you can't think of any way to disprove if it happened to be wrong, then you have to have that conversation explicitly and either amend or discard that hypothesis. And that sort of keeps everybody on the same page about what's being considered and what's not being considered.
Any other questions? Right here in the middle.
In the process where you iterate on like potential issues, and you all get in a room and you all dive down, what are some changes that eventually result in the actual observability stack? Whether it's gaps in logs or metrics or tracing, or too many monitors on the dashboard, what are some of the changes that usually result from that?
What are some of the common changes, I guess, that result from these? Is what you're asking? Yeah.
From iterating over the, yeah. I mean, what I find usually happens is that the issue. Well, so the issue gets fixed, and then, like I said, when the next issue that happens, hopefully, is not the same issue, so you have to start all over again. But the changes that people what people find out is that they were usually initially entertaining too many of the symptoms. Some of the symptoms that they talked about in the incident response were really part of the problem, and others were just things that they happened to notice while they were looking, right? So so the dashboard. So usually you end up with some of the action items from your postmortem are changes to the dashboard, and if you have gone through this process and learned from it, those changes to the dashboard or the log search or whatever end up being ones that reduce the amount of symptoms shown to a manageable size, rather than increasing the size of the dashboard by just adding more things, right? I think that's a sign of a healthy deductive process that's working right.
Awesome. One more question. I do not want to breach my runtime SLO.
So what's the ideal frequency for an engineer being on call? Because I feel like there's always concern that if you're on call too seldom, these dashboards almost look foreign to you when you are on call.
Yeah, so what's the ideal frequency for being on call versus like not being on call?
I mean, the ideal frequency for being on call is never. But I think that it's often we incorrectly couple the concept of being on call to the concept of needing to investigate anomalies in the data that we have. So you need to have I think that we should all have a recurring, consistent way to investigate stuff that looks weird that we participate in together, even when that thing is not an emergency. So that, because that allows us to prevent incidents instead of waiting for an incident to happen and learning from it from the postmortem. So I would encourage, I know that doesn't quite answer your question, but I think I would encourage you to decouple the idea of responding to emergencies from the idea of understanding what the data is trying to tell you.
Awesome. Let's give another big round of applause to Dan. Really appreciate it. Fantastic talk.